All right, continuing on with another example of calculating reaction enthalpy from bond enthalpies. Okay, so what we're going to do here is we're going to take a look at this reaction, and we'll be given a list of bond enthalpies. Okay, so for example, a CH bond has an enthalpy of 413 kilojoules per mole. A oxygen double bond is 498 kilojoules per mole. Carbon-oxygen double bond, 799 kilojoules per mole. And an oxygen-hydrogen bond is at 467 kilojoules per mole. Okay, so I said before it would be useful to draw pictures of your molecules. So doing a sort of crude picture for each one will suffice if you just show the right number of bonds and the right kinds of bonds. Your picture doesn't necessarily have to be stellar. So I've got one CH4, I've got two oxygens, I've got one carbon dioxide, and I've got two water molecules. All right, so let's take a look at the bonds broken and the bonds formed. Okay, so on the right-hand side of the equation, I have no carbon-hydrogen bonds. Okay, so I know for a fact that I'm going to break all of my carbon-hydrogen bonds. So break, 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 break. I also have no oxygen-oxygen double bonds in my products. So I'm going to be breaking both of these as well. Right? So all of the bonds that we see in the products are brand new. So we're going to make that one, that one, that one, that one, that one, and that one. Okay, so we're breaking all the bonds and we're making all the bonds, which won't necessarily always be the case. Sometimes you'll have the same thing in the products. Okay, so you don't necessarily have to break all the bonds and make all the bonds. So we have 4 times we're breaking carbon-hydrogen bonds. We're breaking 2 oxygen bonds. We're making 2 carbon-oxygen double bonds. And we're making 4 oxygen-hydrogen bonds. Okay, so we are breaking, making, and making. All right, so I'm going to take the sum of my breaking, so 413 kilojoules per mole times 4 moles of bonds, plus 498 kilojoules per mole times 2 moles of bonds, minus 799 kilojoules per mole times 2 moles of bonds, plus 467 kilojoules per mole times 4 moles of bonds. Okay, so this is our bonds broken minus our bonds formed. All right, so we should come out with an answer for the delta H of reaction of negative 818 kilojoules. Okay, so our next topic is electronegativity. Okay, and for that we're going to use the Pauling electronegativity scale. Okay, and what's useful about this type of scale is that it shows us how the trend fits with the periodic table. Okay, so the trend for electronegativity follows Z effective. Okay, it also follows ionization energy. Okay, so as Z effective goes up, ionization energy goes up, electronegativity goes up. Okay, so fluorine here is the most electronegative atom on the table. Right? And francium, down here in the bottom right, is the least. Okay, so even if you didn't have these numbers, you would be able to tell who is more electronegative just based on their orientation to where they are in relation to fluorine. Okay, so why do we care? The reason is that electronegativity affects how electrons are shared. Right, so if I have, for example, a hydrogen-fluorine bond, okay, it's a covalent bond, so the electrons are shared, okay, but they're not shared equally. Fluorine is way more electronegative than hydrogen. So if I were to draw sort of a representation of how the electron cloud is around this bond, most of the electrons spend most of their time around the fluorine. Okay, fluorine is much better at pulling the electrons toward it than hydrogen is. So fluorine has the negative end of the bond, and hydrogen has the positive end of the bond. Okay, and what we're going to do is we're going to use an arrow to show the direction of the negative charge. Okay, so the arrow points in the direction of the negative end of the bond, and we have this little crosshatch on the arrow which sort of looks like a positive symbol, so that shows you which end of the bond is the positive end. Right, so what I can do though is I can quantify this a little bit. So I can use these values in the Pauling scale and take the difference. Okay, so if I have fluorine and hydrogen in a bond, fluorine has a 4 on the Pauling scale, hydrogen has a 2.1. So the difference is a 1.9. Okay, so 1.9 in favor of fluorine. Okay, so that's how I know that the negative sign is going towards the fluorine. So we have basic regions of how to decide whether or not a bond is nonpolar, polar, or ionic based on this difference in electronegativity. So the general scale for that, if your difference is between 0 and 0.4, you have a nonpolar bond. If the difference is 0.5 to 1.9, you have a polar bond. Okay, and if your value is greater than or equal to 2, you have an ionic bond. All right, so let's take a look at how that plays out. So if I have, as my example, lithium chloride. All right, we know that it's ionic because it's a metal bonded to a nonmetal. We've talked about the bonding in that compound, in that the electron gets transferred from the lithium to the chlorine. So let's take a look at this in terms of the Pauling electronegativity scale. So lithium has a value of 1, chlorine has a value of 3. So that gives a value of 2.0 in favor of chlorine. All right, so the difference in electronegativity is so great that chlorine quite literally pulls the electron right off of lithium. Right, on the other hand, let's look at another covalent, chlorine. So I have Cl bonded to Cl. We have a 3 for each one. So I have a 0 difference. So this is a nonpolar bond. Okay, you have to have a difference in electronegativity in order to have a polar bond. And in fact, from our general scale up here, some difference is necessary, but we do need enough of a difference in order for this to be classified, or a bond to be classified as polar. Okay, so that's going to do it for Chapter 9. Not a very long chapter. Chapter 10, we're going to get into drawing molecules and doing Lewis structures for entire molecules. So I hope this has been helpful and informative, and we'll see you soon.